Welcome everyone to, I think, our 10th lecture in Chemistry 51C here at UC Irvine. Well, I was cooking this past weekend, putting some leftover spring break ham on a frying pan to warm it up, and it gets this wonderful brownish patina on it that just adds so much flavor. Not healthy, I'm sure. And I wanted to talk about the chemistry that underlies the browning of foods. When you sear a steak on the outside, it gets these wonderful brownish colors, either on the barbecue or in a pan. When you fry French fries in oil, or when you bake bread, there's this brownish color that appears on the crust that is responsible for so much of the amazing flavor and the complexity of those foods. And I want to talk about the chemistry because the chemistry is complex. It involves the chemistry of carbohydrates. We have a whole chapter on carbohydrates in the textbook that we use, and the chemistry of amines. And we have a whole chapter on amines in our textbook. And we'll be covering that chapter on amines in particular. But the chemistry of browning relates to the chemistry of iminium ions. And that's the subject for the chapter that we're talking about today. So let's go ahead and talk about what's behind all of these, the chemistry of browning. It's a reaction called the Maillard reaction, and really interesting chemistry. So the Maillard reaction involves chemical reactions of glucose primarily, or other sugars related to glucose. Glucose is one of the carbohydrates, the main carbohydrate that the human body uses as the currency for metabolic energy. And it's present in all kinds of sweet tasting foods, or sugar related compounds are present in all types of foods as a basic nutritional component. And also there's a reaction with amines. And every time you've eaten some protein containing food, there will be primary amines dangling off the surface of those proteins. And so when you heat at elevated temperature sugars, carbohydrates with amines, you get this bond forming reaction where you go from C double bond O, which is an aldehyde on a sugar compound, to C double bond N. And we refer to these compounds with C double bond N as imines. And it has not been a major discussion so far in the first year organic chemistry course here at UC Irvine. Let's talk about the mechanism for that reaction. So what's happening to the amine groups that are dangling off the surface of a protein as they begin to react, or free amino acids, I'm not sure those are as important, and the reaction with the aldehyde groups that you find on monosaccharides. It's a particular class of carbohydrates. Okay, we're going to be talking about this mechanism in more detail, maybe in this lecture, but what's going on in your frying pan, or in the French fryer, in the oil in the French fryer, or when you're baking that bread, is that the amines that are present on the proteins, like gluten in wheat, or proteins like actin and collagen that you might find in meats, as they react with glucose or derivatives related to glucose, there's an initial attack of the amine on the carbonyl group. Amines are nucleophilic. They like to attack aldehydes and ketones. Aldehydes are extremely reactive. And so you'll get this Switterionic intermediate where you have two heteroatoms attached to the same oxygen atom. Let me just do a little check here and see if, whoa, something just happened. I don't know what just happened. I have no idea what just happened there. So you'll get this initial reaction to generate a Switterionic intermediate, and that protonates. So generally in these reactions, you'll have proton sources that can serve as acids or as conjugate bases. So initially you protonate the O- of this Switterionic intermediate. And then in a second step, that's this second reaction arrow here, you then pull the proton off the bottom ammonium ion. And so that generates this intermediate called a hemiaminal. Anytime you have two heteroatoms attached to a single sp3 carbon atom, those tend not to be stable to acidic conditions. And so when you protonate this oxygen atom, this hydroxyl group, it turns it into a good leaving group, and the lone pairs on nitrogen can then push that out. And that generates this key intermediate called an iminium ion. This is really the crux of this mechanism. Iminium ions are so promiscuous. They do so many things. When you pull the proton off that I didn't draw here on this carbon atom, at this carbonyl carbon, there's a CH I didn't draw. When that gets pulled off, it generates a highly reactive species called an imine. We're coming up to those in a couple of chapters. And that leads to this series of reactions that cause carbon-carbon bond formation, dehydration. You generate conjugated double bonds which absorb visible light at all kinds of wavelengths because there's so many different compounds. And that's what leads to the brown coloration. Probably the least interesting thing that could happen is you deprotonate the nitrogen of the iminium ion to form a neutral imine. That's not at all an interesting compound. It's kind of a stable linkage. It's only interesting when you put the proton on there. These are the really, really reactive species that do a lot of things. I left off on Friday giving you a broad overview of what this chapter was about and trying to put it into context of how it fits into the previous chapter. We've been talking about the chemistry of carbonyl compounds, and we spent so much of chapter 20, our last several lectures, talking about the reaction of supernucleophilic compounds like that form carbon-carbon bonds and carbon-hydrido bonds between carbon and hydrogen. Organometallic reagents like organomagnesium reagents, organolithium reagents. We brought back sodium acetylides as carbon-carbon bond forming reagents for adding to carbonyls. We talked about hydridoborate and hydridoaluminate reagents, and we even talked about organocuprate reagents that I don't have here. And in this chapter, we're going to be talking about weaker nucleophiles adding to carbonyls, amines, way weaker as nucleophiles than organolithium reagents or Grignard reagents, or cyanide anion. We'll talk about that first coming up in a few maybe a few minutes, in about a minute. And then finally we'll get to hydroxyl nucleophiles, oxygen-based nucleophiles that are so weak that you have to protonate the carbonyl in order to get the oxygen nucleophiles to attack. So that's really what we're talking about here, mainly in this chapter. And then they stick in this concept of phosphonium ylides that doesn't really fit anywhere. It didn't have a home, so they jammed it into this chapter, which kind of disrupts the flow of what this chapter is about. So we're going to start off by talking about conditions where, let me just remind you that previously we talked about addition of organolithium and hydrido reagents to carbonyls, so you generated alkoxide products that had to be protonated in the workup in a second step, after all the CC bond formation was done. Now in this chapter, we're going to start off by talking about conditions where we include the acid in the reaction mixture, mild acids, and that's acetic acid, or generally for the amines, and hydrocyanic acid for the cyanide compound. Let's go ahead and get into that and talk about these weaker nucleophiles and how you can actually have proton sources present in the reaction mixture as an essential part of the recipe. So the first reaction we're going to be talking about is a carbon-carbon bond forming reaction, but it involves a nucleophile that is super specific. So if you take some sort of an aldehyde, I'll take benzaldehyde as an example, but it could be any aldehyde. It could even be glucose if that's what you wanted. And we need to add a reagent to this. And I'm going to add, the reagent that we're going to add is, I'm going to write it over here in the corner, just presuming that there's room, is HCN, hydrocyanic acid. Hydrocyanic acid is something you can't buy as a solution. They don't sell hydrocyanic acid as solutions. You can buy it as a gas, but nobody wants to use that as a gaseous reagent. So we make this in the laboratory by mixing two chemicals together, but you're really just making HCN. So we mix sodium cyanide, which is a white powder, with hydrochloric acid. And the hydrochloric acid protonates the cyanide anion and generates HCN. So we're simply doing this because it's not convenient. They ought to just tell you HCN. It's kind of none of your business how you generate the HCN, whether you bought a bottle of the gas and bubbled it in, or whether you make it yourself. This just adds to the seeming complexity of this reaction. You need to write these two components of the reaction recipe, both the textbook, the sapling online problem sets, they all show these two reagents instead of the ultimate reagent you're trying to generate HCN. And when you do this, you add the elements of the H and the CN across that C double bond O. And so you end up generating a functional group known as a cyanohydrin. Now, in this particular instance, we're going to end up with 4 different groups attached to this product carbon. We need to recognize that we formed a new stereogenic center. I'm more arbitrarily going to draw this new carbon-carbon bond with a wedge, but I could have drawn it with a dash. I could have drawn any of these bonds with a wedge instead. It's arbitrary. I just want to indicate that I've generated a new stereogenic center plus the mirror image. So as long as you figure out a way to indicate that you end up with a mixture of enantiomers, of mirror images, then you're displaying correctly what's going on. And again, this particular species is known as a cyanohydrin. So it's a kind of a strange way to generate a very specific type of carbon-carbon bond, a bond to a nitrile functional group. This functional group, if I haven't said it, is also called a nitrile. And we'll be talking more about those nitriles, those cyano groups, nitrile functional groups, in the coming chapter. Okay, let's go ahead and go through the mechanism for this reaction, because you need to run these reactions under acidic conditions. Hydrocyanic acid is, if you just bubbled it in, that would create acidic conditions. In this case, you've got enough hydrochloric acid to make the conditions net acidic. So let's go ahead and draw out the mechanism. You take some sort of a carbonyl compound. It could be a ketone if you wanted. Could be acetone, could be cyclohexanone. And then we add in our nucleophile. And this is a strong enough nucleophile, the cyanide anion, that it will directly attack. So let's go ahead and draw that coming in and attacking. I like to use, for some reason, I like to use my red arrows for mechanistic arrow pushing. So we push the electrons up to the carbonyl. Hope you're getting used to that pattern of reactivity where nucleophiles attack carbonyls. That's really a super important component of our course. And now I've generated a new carbon-carbon bond. There we go. Brand new carbon, and I've added this nitrile functional group. These compounds tend not to be stable, but that doesn't matter because there's acid floating around in solution. The conditions for this reaction have to be acidic in order to get this reaction to work. And so in the last chapter, in the last section where we were adding organolithium reagents and organomagnesium reagents, these alkoxide intermediates built up. And then we came back after lunch or came back later and we dump in a bunch of water to work up the reaction. For HCN addition, hydrocyanic acid addition, you have to run the reactions under acidic conditions so that you protonate this intermediate, this alkoxide intermediate as it is formed. So it's critical to have acidic conditions for this reaction. You can't come back and add a proton source later or the reaction wouldn't work. And so this is the mechanism for the reaction. It's a 2-step reaction mechanism, but it's all occurring in the same reaction mixture. So this initial step is really an equilibrium. The O- will push back out the cyanide if you don't run the reaction, this top reaction recipe under acidic conditions. Now, why would somebody want to add a cyano group? Cyano groups are not that common. They're not that common in nature. They're not super common in drugs. There are some drugs that have cyano groups in them. Paxil, I think, is one of the antidepressants that might have a cyano group in there. Let's go ahead and take a look at one of the major transformations that is very common to affect with a nitrile functional group. So let's go ahead and first practice using this cyanohydrin forming recipe. We'll take cyclohexanone and we'll just imagine that we form a cyanohydrin with that. And our recipe is to use sodium cyanide and hydrochloric acid. That's the super common recipe that everybody uses. So sodium cyanide and hydrochloric acid. And these reactions are efficient at room temperature. If I don't say otherwise, anything about temperature, you should always assume that the reaction conditions are room temperature or ambient temperature, as we say, ambient conditions. Now, this cyano group can be hydrolyzed with a secret transformation, and we're not going to tell you the mechanism for this transformation. So I'm not a big fan of teaching you reactions and not telling you how they work. It's just a very long mechanism that you're not prepared to think about even until the next chapter, until the next section of the course. Here's the conditions that we're going to see for hydrolysis of this, and you're going to see the same hydrolysis recipe. Hydrolysis meaning you cleave bonds and add the elements of water. And our recipe is to use 6 molar HCl, 6 molar hydrochloric acid. Why 6 molar? It's because we buy bottles of 12 molar concentrated hydrochloric acid, and if you just mix it 1-to-1 with water, 1 part water, 1 part conc HCl, you get 6 molar. So that's why that's a particular number. Basically what I'm telling you is it's almost super concentrated saturated HCl, but not quite. That's very concentrated 6 molar hydrochloric acid. But what makes this reaction work, if you just put this cyanohydrin in 6 molar HCl at room temperature, it would just sit there. It would sit there for days, it would sit there for weeks. So to get this reaction to work, you have to boil it. And if you don't boil it, nothing will happen. And if you don't write 100 degrees or boiling or something to indicate that you have to heat the heck out of this, I would count that wrong. That's not the correct conditions if you don't indicate how important it is to have this occurring at elevated temperature. So that reaction recipe that I'm telling you converts a somewhat unusual nitrile functional group into a very common hydroxy functional group. So, and that's very common. It's common in nature, like in pyruvic acid. I think you guys who have taken biochemistry might know about pyruvate and lactate. But having hydroxyl groups directly next to carboxylic acid, citric acid is one of those, is a very common functional group in drugs and in biochemical species. Now, again, I don't ask you to know the mechanism. The book doesn't tell you the mechanism. It's a 12-step mechanism. I don't want to grade on an exam your attempt to write out a 12-step mechanism. So it's a cool mechanism, but we just don't have time to cover that. And it's there, and you cover that kind of chemistry in the next chapter. So why do they, I'm not sure why they tell you about this transformation here in this chapter. But again, I've tried to indicate that in the 5th edition of the textbook, you'll see that those kinds of transformations coming up. Just go look in your textbook on hydrolysis of nitriles, and you'll find information about that. All right, for some reason, the book just out of nowhere throws this reaction into the mix, and it doesn't really fit in. And I'm going to talk about it. It doesn't really fit in anywhere in this chapter, but they've jammed it in here. And so I'm going to try to follow that a little bit in order. I'm going to introduce you to a carbon-carbon bond forming reaction that involves a species of reagents that is just completely freaky to you and is nothing like the organolithium reagents in terms of the look and the structure. It's nothing like the oxygen and nitrogen nucleophiles in this chapter. But for some reason, they've put it in here, and it's really a reaction that was dominant in the last century, not in this century. It's a reaction for making alkenes. A particularly common transformation that you want to do as a synthetic organic chemist is convert CO double bonds into CC double bonds. So suppose you had this carbonyl and you wanted to convert it into, instead of a CO double bond, a CC double bond with a methyl group hanging off of that. How would you do that? Turns out there's a reagent that does that. And the reagent has, there's a carbon, a hydrogen, and a methyl group here, would have something like CH, and then I guess I would put Me here for methyl. Me bonded to a phosphorus atom. But that phosphorus atom has some particular substitution on here. It has 3 phenyl groups. So all right, PH3, that's the abbreviation for phenyl. It's like a phenyl substituent. There's 3 of them on this phosphorus atom. Imagine how complex it would be if I asked you to write out all those phenyl groups. That's a lot of business there. Okay, so we're not done with the chemical structure of this reagent. It also has a plus and a minus on adjacent carbons. So, and let me just indicate that there's a lone pair on that carbon atom. This is the chemical structure of the reagent that you add in order to convert CO double bonds into CC double bonds. That turns out to be valuable because you know a bunch of reactions that you can do already with CC double bonds. You can do hydroboration oxidation sequences. You can add Br2, you can add Cl2, you can add HCl and make a tertiary alkyl chloride and then convert that into a Grignard reagent. Once you have an alkene, the number of synthetic options that you have is actually quite expansive. So it's valuable to make alkenes. The problem with this reaction is you don't get great stereo control. And what do I mean about stereo control? I'm not talking about enantiomers or diastereomers. I'm talking about double bond geometry. If you look carefully here, this particular double bond geometry has the methyl and the ethyl on opposite sides. So this is the E geometric isomer of that alkene. There's a stereochemistry here. It's not RNS stereochemistry, it's E versus Z for the alkene. And you don't get good control in this reaction. You actually get mixtures of double bond stereoisomers. And that's kind of a problem here. Nobody really wants to get mixtures of stereoisomers. Maybe that's why this particular reaction has tended to fall out of favor with synthetic organic chemists who like to take one set of starting materials and get one set of products. So let me just clearly indicate that you get a mixture of E plus Z, and you can't stop that. And if I tell you to write the products out, I want you to write both the E isomer and the Z isomer. If it's unambiguous, you can just write one and write plus Z, but make sure you get it right. Don't write the E and say plus E, because first of all, that's not, don't get it confused with plus E enantiomer. These are E and Z olefin isomers. The other byproduct of this reaction, which is not important, we throw it away, is you get this byproduct, triphenylphosphine oxide, that has this magnificent PO double bond. Wow, that's really a super driving force. Okay, there's a name for this particular type of reagent where you have P plus next to C minus. This one is called a Vidiq reagent, named after Georg Wittig, who invented this class of reagents and this particular transformation. So that's a Vidiq reagent. Okay, so that's kind of, anything that gives mixtures of E and Z isomers is not very useful. I don't like to go into the laboratory and set up reactions when I know they're going to give me mixtures of compounds, because you almost never want two different compounds. It's hard to work with them and purify them. I like reactions that give one product when I mix my reagents together. So if you're careful about how you use the Vidiq reaction, you can choose starting materials so that you only get one product and not mixtures of E and Z. Let me give you an example. Let's take an example of a ketone that has two of the same functional groups on the carbonyl, methyl and methyl, acetone. Since you have two functional groups on the carbonyl, it won't matter whether you get a cis or a trans isomer in this reaction. Let me go ahead and take an example where I take a Vidiq reagent. You always have pH3P. And what varies here is what's bonded to the other side. So let's suppose I have, on this other side, a phenyl substituted carbon atom. And I'll talk about this plus and this minus. That's probably making you really uncomfortable, but we'll resolve that in a little bit. And so in this particular Vidiq reaction, we'll end up with some of the product with the phenyl going down, there's an H atom going up, and then the other isomer. But because there's a methyl group on both sides of the other carbon here, there's no difference between this and the double bond isomer. The E, there is no such thing as E and Z unless both of the carbons have different functional groups on them. And that's how you get an E and a Z. So if one of the carbons has two of the same functional group, you can't distinguish one double bond isomer from the other. Here would be another example. This one is a little bit more, I think a little bit more obscure, where we do a Vidiq reaction on this carbonyl here. And in this case, we're going to have two of the same groups on the Vidiq reagent, on this phosphonium ylide reagent. So here's our phosphonium ylide, and I'll pick a very particular one where we have two H's on that carbon atom of the Vidiq reagent. And so in this case, we would end up generating a CH2. I'll go ahead and label the CH2s. There's the CH2, and this can't exist in that. There's no cis and trans for this double bond here. right? Because if I exchange the positions of the H's, you wouldn't be able to tell the difference. So if you're careful about your reagents, careful about either your Vidiq reagent or about your starting carbonyl compound, then you can avoid this issue of mixtures of getting mixtures of E and Z isomers. And no chemist wants to get mixtures of E and Z isomers. Let's talk in more detail about these Vidiq reagents, because it's kind of freaky to see that plus and that minus next to each other. Well, why would I draw it like that? Let me go ahead and draw a picture of this phosphonium reagent. So I'm going to draw this, this phosphonium ylide, a phosphorus ylide, and I'm going to be careful to make sure that I have a plus and a minus on adjacent atoms. This is called an ylide. Anytime you have a plus and a minus on atoms directly bonded to each other with nothing in between, no atoms in between, we refer to that as an ylide. And as long as I don't do something silly like violate the octet rule, in theory, I can draw a resonance structure where I take these electrons and donate it in. And I'll explain the issue with why we why we often choose not to do that. If I did that, I would end up with a completely valid, in theory, a valid resonance structure. Boy, I got all these phenyl groups attached to this phosphorus. I used to get confused when I took this class a long time ago. I used to get confused about the P's in the abbreviation phenyl with the P that's the symbol for phosphorus. Those are nothing like each other. This is not phosphorus hydrogen. This is a phenyl group. Maybe I should have drawn out the whole 6-member benzene ring here so you wouldn't get confused, but it would take up the whole page. And when I donate this lone parent carbon into phosphorus, I'll have a resonance structure that's quite easy to draw. Why don't we draw it this way? I don't have to draw all those charges. The reason why this is not a very good resonance structure is because phosphorus is a third row atom. And the orbitals on phosphorus, the empty p orbitals that you would donate into are huge. Those are big p orbitals. They're not the right size for making stable double bonds. You form stable double bonds only between second row atoms. Carbon-carbon double bonds, carbon-nitrogen double bonds, carbon-oxygen double bonds. Those are stable pi bonds. Double bonds to third row atoms are not very stable. So just because of this mismatch in orbital size, you don't get a very stable double bond here. This pi bond that you generate through donation is weak pi bond. And because of that, the carbon has a lot of carbanion character. This is actually a pretty good resonance structure. There's very little pi character in that bond that I drew. So it reacts as though it's C minus P plus. And so that's why many people, myself included, if I can remember to, I draw it as the P plus C minus resonance depiction. They're the same molecule, we're just depicting them differently in these two ways. And drawing it as P plus C minus, drawing it as an ylide structure, really emphasizes the fact that the carbon atom is nucleophilic. Where do you get these Vidiq reagents from? I'll show you how you synthesize them. You synthesize them using an SN2 reaction. SN2 reactions are not very good, so you're kind of limited in your ability to make these by whether the SN2 reaction is, if you can't do the SN2 reaction, you're not going to be able to make the Vidiq reagent. So generally, you're kind of restricted, not totally, but these reactions really only work in super good, reliable yield when it's with a primary alkyl halide. You can get it to work a little bit with secondary alkyl halides, which are not very good for SN2. And in this particular case, you'd have to heat these. So if you take a typical phosphorus compound like triphenylphosphine, super inexpensive, you can buy buckets of this stuff, and you heat the heck out of this to get this SN2 reaction to go. You can get this to undergo an SN2 reaction with primary alkyl halides. And a common one would be methyl iodide. Methyl iodide is very reactive towards SN2. There's no competing elimination reactions. The product you would get if you follow my arrow pushing is going to end up with a positive charge on phosphorus. So if I start off with 3 bonds to phosphorus and I use that lone pair to attack, I'm going to end up with a positive charge in my next structure. So there's 3 phenyl groups on the phosphorus. I'm not going to draw out those phenyl groups. And then here we go. There's the positive charge. And I'll have this R group attached to that CH2. And the X minus will be floating around. It'll be either an iodide counterion. It might be we call this a phosphonium salt when there's a P plus and a sort of a counterion that's adjacent to it. And you can isolate these and purify them. And then the key step here is you treat these with a powerful base. And there's only one base that we're going to teach you in this quarter that is reactive enough to deprotonate a phosphonium salt like this. There's 2 hydrogens here that can be deprotonated. Here's one of them in this species. Here's the other. There's no, if I look at the carbon atom on the phenyl that's attached to the phosphorus, there wouldn't be any H's directly attached to the carbon on the phenyl group that's bonded to the phosphorus atom. So if I treat this with a super reactive base, N-butylithium, wow, that is strongly basic. It's also a nucleophile, but there's nowhere there's no carbonyls in here. There's no way we can do a nucleophilic attack. There's no way to, really the only reaction that we can do here is to deprotonate one of these H's. And that's what happens. And this is the only base that will do that. You can't draw a base. You can't draw sodium hydroxide. None of those are appropriate. You have to write N-butylithium as your reagent. And why do we use N-butylithium? It's super powerful and it's inexpensive and commonly available in every laboratory. And so that's how you generate this phosphorus ylide here in this reaction. So you deprotonate using this bond here. We'll deprotonate that. And it generates the phosphonium ylide. And if you wanted, you could draw the resonance structure for that. I think sometimes when I'm trying to abbreviate really, I'll just draw the P double bond C, and I'll write this as a molecular formula. 3 phenols attached to a phosphorus. And this is the thing that you might make mistakes with. You might write P3PH or something. It's easy to get those confused. Okay, so that's how you make a Vidiq reagent. You do an SN2 reaction on an alkyl halide, and then you deprotonate with butylithium. That's the way that works. Let's go and take a look at the reaction mechanism for how you generate CC double bonds using Vidiq reagents. Okay, let's go ahead and start off by, I'm going to take a carbonyl compound and I'm going to take a Vidiq reagent and I'm going to try to line these things up next to each other so you can see where these components come together. And I'm going to draw the Vidiq reagent up and down here. There's that long phosphorus carbon bond. Here's the 3 phenyl groups that are attached to the phosphorus. There's my lone pair. And there's the plus. And the mechanism for the Vidiq reagent involves 2 bonds forming at once. First of all, I'm going to form a carbon-carbon double bond by using the lone pair on this CH2 minus to attack the carbonyl. And as I break these pi electrons, instead of giving them to oxygen, I have to break one of the 4 bonds to this carbon atom. I can't end up with 5 bonds on a neutral carbon atom. I'm going to have to take those electrons and do something. Instead of giving them back to oxygen, I'll use them to attack the P+. So as this carbanion gets closer and closer and closer to the carbonyl carbon, the O-, as it develops, as you develop an O- charge, it'll get closer and closer to the P+. And you'll end up forming both of those bonds at the same time. And you'll end up with this completely uncomfortable and weird intermediate. Let me draw the, maybe I shouldn't have used 2 phenols here because I have so many phenyl groups on this structure. It's a little bit confusing. These were the 2 phenyl groups on the carbonyl compound. But I'm going to generate an oxygen-phosphorus bond, and I'm going to generate a carbon-carbon bond, and I don't break the PC bond, that's still there. So let me go ahead and draw that. So I generate 2 bonds at once, and remember, there's 3 phenyl groups on this phosphorus, PPH3. That might look weird to you. You might think, oh, you can't have 5 bonds to phosphorus. Of course you can. Phosphorus is not a second row atom. Phosphorus is a third row atom. And if you look at the structure of nucleic acids like DNA and RNA, every phosphorus atom in the backbone has 5 bonds. That's completely usual to have 5 bonds to phosphorus. You can also have 3 bonds to phosphorus. We're not going to go into phosphorus chemistry in detail, but no problem having 5 bonds to phosphorus. I know that looks weird to have 5 bonds. Just get over it. That's what makes, I'm not saying that's stable to have 5 single bonds to phosphorus. That's called a species called a phosphorane, but okay, that's not there's ring strain in that 4-membered ring. And this P really wants to be on its own. It wants to leave as a P double bond O. In so many reactions in organic chemistry, the main driving force that we're using to drive the reaction forward is formation of PO double bonds. That's why DNA is stable. So there's an expulsion reaction where this phosphorus, the CO bond is going to cleave and give the electrons to the phosphorus. And at the same time we do that, we take these electrons over here and we form a CC double bond. You could draw this arrow to end in the middle of the double bond, or as I'm doing it to attack the atom. I'll accept either way. Just be very specific about how you draw that. Don't be wishy-washy. Either attack the atom or make the arrow end in the middle of the double bond. Both of those ways are acceptable, but halfway is not acceptable. So if you look at my arrow pushing, I shouldn't have a carbon-oxygen double bond anywhere in this molecule anymore. And I shouldn't have any carbon-phosphorus bonds. I'm breaking both of those bonds. So what I'll end up with, according to my arrow pushing, is this P double bond O compound, this byproduct that's extremely stable. That's the driving force of the reaction. And I will have generated a new CC double bond. So that's the 2-step mechanism for the Vidiq reaction. It's not a well-drawn geometry there, but you get the idea. I generate a new alkene. Now, this works for ketones. It works for aldehydes. It does not work with esters. It does not work with amides. So if you have a tendency to look at any carbonyl as being identical and the same, they're not. You can't take an ester and form a CC double bond from that ester carbon. So if you feel some sort of compulsion to want to make a CC double bond out of an ester or an amide, that's not going to happen. I'll just write a dashed arrow here and I'll write no, no. So not with esters and not with amides. Doesn't work. That's the key operative term there is it does not, this Vidiq reaction doesn't work with esters or amide carbonyls. So avoid, can't see why you would want to make something that looks like this. Let me show you strategically how to use the Vidiq reaction. I feel like the book is struggling to find reasons to tell you to use this, and it does give you one strategic reason to want to use the Vidiq reaction. So I'm giving you an example. If I tried to formulate a question on an exam where I say, okay, tell me how you would construct this in some way. And I would come up with an example where you couldn't use chemistry you knew before the Vidiq reaction. Here's the way that you might feel like you want to do this. You might feel like you want to start with a carbonyl compound, a CO double bond. Those are readily available. Is there some way to take a carbonyl compound and do the Vidiq reaction on this? And if you look at some sort of a previous chemistry, now that you know the Vidiq reaction, this turns out to be a very easy transformation for you to do. You could take the carbonyl compound, you could take a Vidiq reagent that has an H and a methyl group on it, and then you just mix them together and you'll get a CC double bond. Now, you have other ways to make carbon-carbon double bonds. If you've got a carbonyl group, you could certainly add a Grignard reagent or an alkylithium reagent in a 2-step process. I hope you've been practicing that. I hope you spent the weekend practicing those reactions, and I hope you spend next weekend before the exam practicing those reactions so that you're really familiar with forming carbon-carbon bonds by adding to carbonyls. If you did one of those Grignard additions or organolithium additions, it would be very easy to add a 2-carbon piece, but it wouldn't have the CC double bond. And here's where you're going to run into a problem using only chemistry from last chapter to generate a product like this in high yield. You know some reactions that you can use in order to dehydrate alcohols, in order to give alkenes, POCl3 and pyridine, or sulfuric acid to do dehydration reactions. I'll take that traditional reaction. Sulfuric acid, I can't remember which chapter you covered those types of, this is an E1 reaction mechanism. I'll write E1 mechanism. Who cares about the mechanism? It's a way to dehydrate alkenes. Sulfuric acid is extremely dehydrating. It absorbs water in addition to being a strong acid. The problem with this reaction is not only will you generate the alkene where you eliminate across here, you're also going to generate an undesired alkene that you don't want. There's no way to control whether the protons, let me use a green here, whether the protons come off from here or come off from here. You're going to end up getting both of those products as a mixture. And nobody wants to get, these aren't just geometric isomers. These are constitutional isomers where they don't even have the same chemical structure. It's not a stereochemical difference. The best you can say is they have the same molecular formula here, and that's not what you want. So you couldn't use alkylithium addition and dehydration to efficiently generate just this alkene. Now let's talk about another approach, because there's a different Vidiq reagent that in theory you might be able to mix together. There's another pair of reactants that you could mix together to generate this, if you could make them. And I'm saying if, because it's very hard. It doesn't work well. So if you had this Vidiq reagent somehow, you could get your hands on it, and you added an aldehyde, like acid aldehyde, like this, you'd have no problem getting this. The problem is it's very difficult to generate this cyclohexylphosphonium ylide here. The problem is not doing the deprotonation with butyllithium. That's pretty reliable. If I had this phosphonium reagent, this phosphonium salt, not the ylide, if I was able to get my hands on this, and I treated this with butyllithium, that would work well. The problem is generating this through an SN2 reaction with a secondary alkyl halide. I don't even want to put I shouldn't even put a solid arrow there, because it's just hard to do SN2 reactions on secondary alkyl halides. I can put the best leaving group in the world on here. Well, it's not the best leaving group in the world. Iodide, and try heating this with triphenylphosphine, and it's still not going to be a good reaction, because this is, I'll just write poor here. That's a poor reaction. Don't use a synthetic group that looks like this, because this is a secondary alkyl halide. And SN2 reactions, especially with triphenylphosphine, which is not really a great nucleophile, you can get away with that if it's a primary alkyl halide, but secondary is not very good. So the Vidiq reaction looks really powerful because conceptually, oh, any carbonyl you can replace with a CC double bond, but you have to be able to make the phosphonium ylide reagent, unless I just tell you show reagents you would use to complete the following transformation. If I say just show me reagents, then you don't have to worry about how you make the reagents. As in a synthesis, if I say go from here to here, you don't have to tell me how to synthesize this. On a multi-step synthesis, you just put the reagent, and as long as it's makeable, I'll believe that you can make it. You can't put, I don't know, you can't put some weird species that doesn't exist. Then I'll say, hey, nobody can make that. Okay, this is really what we're trying to get to here. Well, the Vidiq reaction is cool for making CC double bonds, but I started off by showing you this Maillard reaction of amines and aldehydes. I would say that this reaction of carbonyls to form imines, CN double bond, is one of the most important reactions in biochemistry. And so let's go ahead and talk about this reaction that takes carbonyls and forms C double bond O and forms C double bond N. I'm going to use benzaldehyde as my starting material. just because it's common. And if you take some sort of a primary amine that has 2 H's on the amine, we call that a primary amine. This will be a boring one, methylamine, kind of boring, except you can use it to make methamphetamine. And then you mix these things together, and you have to add a secret catalyst to this. And throughout the book, boy, this makes me a little bit annoyed. Not a little, I'm way annoyed. They keep referring to this in the book as a weak acid, like it's so secret that they can't tell you. And I feel like maybe in the book they're a little bit confused about whether that means a dilute acid or an acid with a high pKa. And those are not the same thing at all. And let me just tell you that in these types of reactions for forming amines, there's one common acid to use, and that's acetic acid. So why don't they just tell you acetic acid? I'll just draw the partial Lewis structure. It's acetic acid, vinegar. Why don't they just tell you that? I don't know. It's pretty simple. So throughout the book, they'll write that. In most other places in the book, when they're willing to tell you, they'll write it out as CH3CO2H. That's the weak acid catalyst they're talking about. I don't want you to, when I ask you for a reagent, you are not allowed to write the word weak acid. I want you to write out acetic acid as ideally as the molecular formula, because it's easy to write out. And let's stop pretending that it's such a secret you can't possibly talk about it. That's crazy. Okay, so this is a general process. So as long as you've got a primary amine, that's a primary amine, we're going to have a whole chapter with amines, is an amine with 1 alkyl group on the amine and 2 H's. So as long as there's 2 H's on that amine, and it's an alkyl group on there, could be an aryl. It just can't be a carbonyl group. Then you can do this transformation. So we take a carbonyl compound, little harder with ketones, actually not a little harder, it's a lot harder with ketones, but you can still do them. It means, what do I mean harder? It means probably you have to heat it at higher temperature, maybe use special tricks to drive the water out. You don't need to worry about that. But we're gonna put in our secret catalyst. We're not gonna write the word weak acid, that's lame. We'll just indicate that you require a catalytic amount of acetic acid. Here I'll write out the molecular formula. That's supposed to be a 3 there. CH3CO2H. That's the molecular formula for acetic acid, although my 3 is pretty poorly drawn. And that forms a CN double bond. And that's the way the Maillard reaction works. You take carbonyl compounds like sugars or carbohydrates, you add amine functional groups that are on protein side chains, and you generate these C double bond N compounds called imines. These are imines. Imine, that's an imine, it's a CN double bond with an imine. Now there is a water byproduct here. I ask you to draw the carbon containing products when I tell you to draw the products of a reaction. So we don't draw the water out generally in these processes because that's not an interesting part of the repertoire of products. Okay, so when we come back on Wednesday, I think, we're going to be talking about the mechanism for this reaction, even though I already showed you most of the steps of the mechanism for that Maillard process. It's the same mechanism as the Maillard reaction. We'll talk about the mechanism for iminium ion formation, such an important transformation for biology, for synthetic organic chemistry, really an important overall process. Okay, we have an exam coming up 1 week from today. It's going to cover chapters 18, electrophilic aromatic substitution, 19, which is the acidity of OH bonds. You really need to know how to explain the stability of the conjugate bases, alkoxides or enolates or phenylates or things that have O- on them. And then chapter 20, which is this chapter with all these hydridoaluminate and hydridoborate and organolithium and organomagnesium reagents. It's such a rich chapter. You really need to know those transformations and know how to use them in synthetic schemes. So keep working those. Even though the stuff we're covering now is not on next Monday's exam, it's going to be on the following exam. Stay on top of the material, keep working problems, and thanks for joining me today.